of Dirichlet L function. So please.
Okay, thanks. I'm happy to be able to speak here, and I will talk about moments of Dirichlet L functions. This is joint work with Rapansan, Dexay, Anri, and Maxime Radeville. So I will start with the most simple case, which is the Riemann zeta function. So just for the basic definitions, so zeta function is defined by the series n2 minus s for real part of s greater than 1. That's when the series converges, and otherwise it's defined through analytic conversion, and this is the simplest possible L function one has. And what I mean by moments are the sort of means of powers of the zeta function. So the 2-gate moment is taking the integral from 0, which is the line where the real part is half, and we take the 2-gate moment on that line. And we have quite good models what this is supposed to be for different values of k. In particular, we expect that for certain constant ck, this gate moment is asymptotic to t times log t to k squared, so that the average value of the zeta function is a bit larger than 1, essentially. And asymptotics are known only for k equal to 1, which is the second moment, and for k equal to 2, which is the fourth moment. And the second moment is due to Hardy and Littlewood, and the fourth moment is due to Ingham. But unfortunately, we don't know asymptotics for any other value of k. 2 and 4 are the only, or for k, 1 or 2 are the only values of k that we know. It would be very interesting to know more, because this understanding the moments of zeta have applications, for instance, to studying the divisor functions and prime numbers, and also to zeros of the zeta function, and so on. And for instance, if we had an upper bound of this form for all k, that would imply the Lindelof hypothesis, which says that the zeta at half is always at most t to epsilon. So these are interesting and important questions. And any progress on the moments would, for instance, improve our knowledge about the times in short intervals and so on. So it's interesting to study the moments. And let me first show sort of how to get an upper bound for a moment of the zeta function, because that will serve as sort of a guideline for working on the Dirichlet L function, which is my main topic. So for any L function, there is a parameter called analytic conductor, which sort of measures the complexity of the object. And for zeta half plus it, it's of size t plus 1. And morally, the approximate functional equation for L functions allows one to approximate at half line the L function by a Dirichlet series truncation of the formulating Dirichlet series with the n going up to square root of the analytic conductor. So we can approximate the zeta at half plus it by a Dirichlet series of n half plus it if we take n to up to t to half. To be precise, we would have to have another term where we have n2 minus half plus it and a twist, but let's just pretend that we have this approximation. And on the other hand, by the mean value, we can estimate moments of this approximation here pretty easily. So let's, for convenience, change the little t to capital T and look at the 2-gate moment of this approximation to the zeta function. Then we have the mean value theorem for Dirichlet polynomial, which says that the mean square of a Dirichlet polynomial is at most the length of the integral, which is t in this case, plus the length of the Dirichlet series, which is t to half to power k, because we are interested, it gives us a bound for the square of the Dirichlet series, times the mean square of the coefficients. And if we look at the kth power of this Dirichlet series, then the coefficients are the kth for divisor functions. So this is the upper bound we get from the mean value theorem for Dirichlet polynomials. And if we evaluate this sum here, it evaluates as log t to k squared. And so this is of the shape that we knew that the asymptotics are for k equal to 1 and k equal to 2. this argument is not rigorous yet, because I'm saying that morally we can use approximate function equation. There are some technicalities, in particular related to the fact that the approximation, the truncation, or a smooth weight here actually depends on the t, and here I want to have the same Dirichlet polynomial for every t, but these technicalities can be, one can make the argument rigorous, and this way one gets the upper bound for the 2k moment by making the approximation to the zeta by the Dirichlet polynomial and using the mean value theorem. And for k equal to 1 or k equal to 2, this term t to k over 2 is at most t, and in this case we get the correct order of magnitude upper bound. But if k is larger than 2, then we don't anymore get the correct order of magnitude upper bound. And if one wants to get asymptotics, as Ingham and Hardy and Little would, then it's a bit more difficult. But given this thing here, it's not surprising that we don't know asymptotics for larger values of k than for 2, because this argument fails for larger values. Actually, we don't know upper bounds for larger values because this sort of argument fails. It becomes too complicated, the objects we get. We have a too long approximating series. Okay, so that's what's known about the zeta function. But what I wanted to talk about today is the Dirichlet L functions. So for this, let's define the L functions. We take chi to be a primitive Dirichlet character. And again, we defined ls chi, the Dirichlet L function, by a series. Then the real part of s is greater than 1, the series of chi n over n to s. And it has also an Euler product. And for other s by analytic conversion. And now one can ask moment questions in two different aspects. There's the Q aspect, the conductor of the character, and there's a T aspect, which is if we look at S equal to half plus IT on the critical line. We can ask moments where we integrate over T, or we can ask about moments where they take averages over chi or over chi and Q. And in this case, the analytic conductor is Q times T. That's the complexity of the L function. And in this talk, I will concentrate on the Q aspect, and I will almost fix S equal to half. I will later explain what I mean by almost fixing it. But let me mention in this context that also Balasubramanian has some work in the early 1980s about the second moment of L half plus IT chi. So he was taking an average over chi, but it wasn't at point half, but half plus IT. And this was mentioned also in Sparking's talk on yesterday. Anyway, I will concentrate on the Q aspect here. And so I will first talk about what if we average over chi, what happens then. So in that case, the story is quite similar to the zeta function. We can do the fourth moment by work of sound. He has shown an asymptotic formula for the fourth moment when we average all the characters chi, and it's of shape q log q to the 4. Then this is again k squared, 2 squared here. And Heath-Brown showed this in the case then q doesn't have too many divisors, for instance, for primes, and then sound extended it to for all q. And the second moment was known already before this. And again, we can use the similar sort of moral argument using the approximate functional equation. So with this, we can approximate the L half chi by a series where we have the chi n over n to half. So this is the defining Dirichlet series or Rafter series. And again, we have to take n to go to up to the square root of the conductor. Remember that the conductor was about q times t, but now we are looking at the case of t equals to 0. So the conductor is just q. And again, if we look at the points of this approximation here, we can use the large sieve. It's actually also, in this case, just orthogonality of characters to show that if we take the 2k moment of this series here, we get an upper bound, which is the number of characters, q, plus the length of the sum whose means we are looking at, and it's q to k over 2. And then we have the mean square of the coefficients, and it's again log q to k squared type thing here. And one can make this rigorous. Now there is also no problem with this depending on t, because there is no t involved. And this can be made rigorous to obtain an upper bound for the fourth moment of the L functions of the same shape as sounds asymptotic, but just an upper bound. And getting asymptotic is more difficult again, but in any case, it's not surprising that asymptotics are only known for k equal to 1 and 2 if one doesn't even know an upper bound for higher k. So that's the in this case, and we seem to be stuck as with the Riemann set function here. But if you look at the characters, we have something we can do. We can add an additional average, I guess. That's what we usually do in analytic number. If we have something that we don't know how to handle, we average and see if we can say something on average. And this is what we have been working on. So we add an additional average over q at moments of the L function at the moments of L half chi, average of the character, but also average of the modulus. And in this case, we have by large sieve again an upper bound for the corresponding approximation for the L1 half chi. And here we have number of harmonics, which is now q squared because we are summing over q. And again, the length of the Dirichlet polynomial, or the polynomial here, is q to k over 2. And we have log q k squared. And now the expected asymptotic for the two-kth moment of L half chi, average over chi and q, is q squared times log q k squared, because we have additional sum of length q. So now actually it seems possible to get results up to k equal 4, because this first term, this q squared, which is of correct order of magnitude, keeps dominating until k equals 4, which is the 8th moment. So you have chances to get into higher moments than, for instance, for the z function, if you get Dirichlet L functions averaged over both chi and q. And then indeed, it's not difficult to get this way an upper bound. We can make the approximate functional equation, use it to approximate this by this series here, and something else as well, but at least the upper bound of the correct order of magnitude comes by this argument. But then it's more difficult to get asymptotics. And this was my getting asymptotics for these moments. So before I will discuss the results, I will have to introduce. So I take chi to be an even, it should be primitive. I forgot to fix this typo, which chi is an even primitive Dirichlet character. So by even character means that chi of -1 is 1. And I'm restricting to even characters just for convenience. There is reasonable methods don't work for odd characters, but in this case, the completed L function has 1 plus 1 here. So I want to have the same form of the completed L function always. So that's why I'm restricted to looking at even characters. I could just as well restrict to odd characters and combine the two results. Anyway, I get capital gamma to be the complete L function, where I have the L function, and I multiply a gamma factor and a factor which is of which has size 1 at the critical line. And we have then the functional equation, which explains the form of the completed L function. Why it's convenient is that now the functional equation becomes that the completed L function at half plus s is root number times the completed L function at half minus s. But in the talk, I don't explicitly refer to this. It's just behind the scenes that's happening here. And one more notation is that I will write the flat in case that I'm summing over primitive and even Dirichlet characters, and I'm writing phi that number of even primitive Dirichlet characters. Okay, so with this then I can start these moments So first, we have these constructors which say that if we sum over characters and take the to-gate moment, we expect that the size is about the number of characters times q k squared. And recall that we had the completed L function where we essentially just multiplied L by a gamma factor. And what Contrivaniets and Sound have managed to prove is for the sixth moment, they have got asymptotic formula. Okay, so there is in the chat how much is asking for others as well. So do you hear all right? Other problems? Can you hear me okay? What is saying is very okay. So the complaint, I will keep my phone, but if it's in, I would hear better if I switch it off. I will do. Okay, I can switch my camera off if it helps, but I don't know if it will help. Okay, I will continue. I'm afraid there's not much I can do about the voice other than switch off the camera. I will try to talk clearly and loudly, but let's see. Okay, so for the sixth moment, Contrivaniets and Sound have got an asymptotic formula, but not for thing like this, average over Q, but they have to add an additional average on the critical line. They are looking at the completed L function, the sixth moment of it at the critical line, and then averaging over chi and Q. And for this, they can get the expected asymptotic formula. This last term comes from the gamma factor in the definition of the completed L function. And what to note here is that in the completed L function, the gamma factor decays very fast. It decays exponentially and with y, so the y average in the
there is some problem.
That's bad. Also, are we not recording this talk?
Yes, we are. Our media committee is recording the talk directly.
Oh, no, I see. From outside Zoom.
Yes.
Okay.
Yeah, I think they are screen recording.
And I think suddenly she is gone. Should I call her on it? Do you want to?
Yeah, of course. So, but how?
Only when they record it, it will also show recording. Then it's
No,
not showing anything.
Yes, media is recording now.
Okay, therefore it won't show here, I see.
No,
okay.
it will not show here.
Yeah, they are screen recording, I guess.
So let me check with her what happened, because she's gone, right, for all of you.
Yes. Do you have her phone number?
Yes, I'll follow.
Oh, yeah, sure. Go ahead.
Can you hear me now? I
Yeah,
should be here.
yes.
I can hear.
Yes, we can hear you.
We hear you, but we don't see
You
your
can- Yeah,
slides.
slides. Yeah.
Okay,
You started screen
just share
sharing,
them
but no show of the slides.
Okay, I will try share them again. Can you see them now?
No.
Not yet.
I don't see anything, but we hear you.
Yes,
Oh, now we see it.
Got it.
Yeah.
Okay, can you see the slides now?
Yes.
Yes.
Okay. So I guess I can try to continue. Okay. So
Yep.
the gamma factor decays exponentially in y.
It's
So
gone.
this is
Slides are gone.
Slides are
Lost
gone.
again.
okay. So Then you can't see my slides.
No, no longer.
Okay, I tried to share them
Yes.
again.
They are back.
Yes.
Can you see them now?
Yes.
Yes.
Yes. Hmm.
Oops.
No.
Lost
Something
everything.
is wrong. Something is wrong with her connection.
Yeah. Yeah, she's no longer with us. Ah,
She's back.
Okay, so it seems that it disconnects and connects immediately again.
Yeah. Kaisha, are you streaming from home or from university?
From home.
Hmm.
I have.
Sometimes a
I
cable
haven't had
connection can
contact.
help. Sometimes the Wi-Fi is the culprit, but probably not. If you are from home, then probably it's not your Wi-Fi.
Yeah. Okay, let me see.
Well, another backup plan might be you send us your slides and we hear you and follow the slides locally. Just thought.
Yes, that is a possibility.
So in chat you
Can
can
you see
send
the
the slides.
slides? I don't know how
Mhm.
I can get the slides to everyone, but
Mhm.
can you see them now or not?
Nothing is shared and nothing showed up in chat either.
Okay, and still nothing. Oh. Can you see them now?
No. Also, are you running Zoom from your computer or from
Yes,
browser? Not from browser, right?
from my computer.
Yeah, but is it downloaded software or did you open
Yes,
Zoom
yes.
through browser? Too cold in Finland. No, but Finland surely. I mean, I'm sure they have the best internet ever. So it's
Yeah, I could try
somewhere
to.
between Finland, some poorer country between Finland and on the way. So Kaisha, we can hear you. So maybe sharing the slides by chat or sending it to, I don't know, Sanoli by email, that might help. Oh, well, she's disconnecting. So let's have something very serious going on.
Can we have the lecture a little bit postponed, all lectures maybe? I hope that is okay with everybody. Then it's okay, we can give us some time to fix it.
yeah.
Yeah, I think she joined back.
She is not visible.
And on the last one on the participant,
Yes.
she's
Ah,
See my slide? Do you hear me?
no, but we see that the sharing of the screen has started, but we don't see yet the slides.
Okay.
It says double click to
I
enter
could-
full screen mode. Maybe just the double click, it will work.
Okay, I could also try connecting with my iPad, but I don't know if that helps at all. But I could try if it works better. But the internet connection is the same, so I'm not sure. Sure, but perhaps I
Yeah,
can
yes, we
Yes.
can see that.
try.
no, we lost it again.
But she is not around.
No, so unstable connection.
In the worst case, maybe we organizers can reschedule.
Shaoli,
Yes.
Shaoli, yes.
Yeah.
Maybe you could maybe you already had a phone call with her.
Okay, let me try to talk to her. Okay.
Yes,
And
try to do
reschedule
that
the
and see what is the best way so that we get the slides. Either she send them to you and you show them, or
So,
as
yeah, if you want to talk,
clearly
then-
suggest,
She is back. She is back.
she upload it in the chat.
Yes, I'm here. I just got my iPad to try it.
Okay, sure. Take your time. Jomot, we can just maybe Kevin is here. Maybe we can tell him that his lecture will be postponed a little bit.
I have not seen Kevin. Kevin, you are here?
Yes, I'm here. I'm here.
If it is
You
okay. to-
understand that
I've been
possibly-
I've been watching the events unfolding
Yeah.
here.
Hi, Kevin. Nice to see you.
So
So I guess for
yeah,
you, it's
I'm,
not a problem if we shift by I don't know 15, 20 minutes your talk. This shouldn't be a problem according
that's
to your
that's
time.
perfectly okay. It's
a bit
it's
difficult for
Saturday
me.
morning here for
That's-
me, and I've already sent my slides to Sonoe just in case, and I can post them if necessary.
Okay, okay,
No,
but I
but
don't,
this one.
So
Okay.
I just hope we can get Kaiser back
Yes, yes, sure.
some point.
Okay, so you can hear me okay, but you can't see my slides, right?
Yes.
Yeah, that's
Okay,
correct.
so perhaps I can, if I put the slides available and you can follow them from there. Let me see.
Yes. So if you send them to Charlie, for example, then she can share her screen with your slides,
Okay,
and you ask
yeah,
when to
yeah,
turn
that
and
makes sense.
what to show. Yes.
Okay,
And you just tell her when she has to add some lines to change the page and so on. Okay, we'll manage with that. Don't worry.
okay.
yes, yes, I can do that. Yeah, that will.
Just a moment.
I got Kevin's slides also.
So for the time being, we have the slides. We see your slides.
See my slides at the moment?
Yes.
Yes.
That's strange because it says that I'm not sharing them at the moment. Okay.
We see we get
So
it
I need to see if I-
unconditionally. Well, it depends on the hardware.
Okay, so do you see me switching the slides?
Yeah, we see we get it
No.
unconditionally.
It's
Only
slides are
condition
frozen.
the hardware works.
Slides are frozen. I mean, if you change the page, we didn't see that change.
Uh-huh.
Okay, I tried to send them, but apparently they are not going. I still have some problems with my connection. That
Then if it is possible, maybe we can interchange the talks and try to figure out in between. Is
Yeah.
it okay?
Yeah. I think
Yeah.
it is a if it is okay for Kasha, then this would be a good point, I guess. Yeah.
yeah, it's okay with me. I'm sorry about the problems.
No,
No.
it's okay. We can
Don't
try to
be
figure
sorry.
out
We'll
in
take some
between.
time to solve it. So there will be Kevin Ford in between the two parts of your talk. Okay.
Okay, that's
Okay.
Okay, so I will
Kevin,
call her
fine
and try
with
to
you
fix
too?
it.
Okay, yeah, just give me a couple of minutes and then
Oh
I'll
yeah,
be ready.
sure.
Yeah.
Well, so this is for possibly the organizers. I see that there is a break. There's a hole in the schedule on Thursday at 4:30 Indian time.
It is fine with us. If it is fine with us.
Does it make sense to ask maybe Kaisa, so she will be cool to check what she has, what is going on, and to give her the full slot on
Thursday.
Thursday.
It's fine with us. If she is okay with it, we can do it. Or it's up to her.
It's fine with the organizers because possibly this would be the best, and she has a full hour and she can organize then her talk. So to remember to remind us of what was the beginning of a talk and go on with the talk and be so possibly in better condition.
Yes,
Okay.
certainly. We should ask.
Uh, Kaisa, I don't know if she hears us, but possibly Shaoli,
I'm here. Yeah.
you can phone to her. Sorry.
I'm still here. Yeah. I
Okay.
can hear you. Yeah. I would be happy to talk on Thursday.
Did you understand what? Did you get the point? What I was suggesting?
Yes, I did, and I would be happy to speak on
Yeah,
Thursday.
I think it's better. It's better so that you are quiet now. And on Thursday at noon European time, you have again a full 1 hour slot, and you manage your talk according to this new condition. Okay. I'm not sure she hears the end, but Shaoli, in any case, you have
I have
you have a
sent her.
phone call.
Yeah, I called her. I think, but she is most
You
likely
call
is
her and you
busy.
explain that. I think it would be
Okay,
the
I'm
best.
here again. Sorry.
Yeah, it's fine with you. Okay.
Yes, I think it's probably the best option because it seems that the connection is very unstable at the moment.
Yeah. So then you see how you are doing, whether you can find a place where you have a better connection, and you have time to solve this question.
Yeah. If
Okay.
it seems
This is the
I
best,
go
so-
to the university. I have never had this problem before with any of the talks I have given, so I
Yeah,
don't know
so
why
that's
it's
okay.
not. But perhaps
don't,
because it's Saturday evening here, so people are using the internet a
Yeah.
lot.
This is quite possible. Yeah. So don't be. So then the next slot will be on a Thursday noon European time. Okay.
16:30. Yeah.
Good.
Indian
Thank
time.
you very much. And well, we're all sorry, but it's fine. Don't worry in any case about all that. So I suggest now that Kevin, we move to your talk. Okay, you are
Yes,
ready for that?
Yeah, I'm here and ready. There's a
Is
I
it
did
okay?
yeah there are some people I know who would be interested in, and I don't see them.
So that is what I was also thinking.
Because
Okay,
they might
so
not
then-
know that my
okay.
talk is
We
starting.
can meet,
early.
yeah.
So we just start your talk at the usual time.
Yeah,
Yeah,
that sounds
Okay.
good.
if we could do that.
We
that
start
is
your talk
only,
at the usual time. Now we simply have a break. Okay?
Exactly. I mean, that's a good idea because there may be many who may be joining at 9:30.
And it's fine. And we start at 9:30 p.m. Indian time.
Okay.
And so on. Okay. And great. Okay. See you then.
Good. Hello, Rama. How are you?
Yeah, fine. And you? You are still young. Wait a bit. Everything will change soon. Okay.
Okay.
Oh,
We'll meet
be
at
back.
9:30.
Yeah, I'll be back with you then.